So now we're going to talk about one specific way you can implement coherence called Snooping coherence. There are two options for how coherence can be implemented. We're going to talk about right now is the Snoop-based way to do it, which requires sort of broadcast media. So this is sort of broadcast protocol. And you all have a directory-based way of implementing coherence, which is more of a point-to-point protocol. So the broadcast protocol, well, think about this as those of your friends on Facebook, they create too much traffic. Every time they do something, they tell the rest of the world, and they have to tell all their friends about everything. They are a broadcast kind of person, while a directory-based protocol is one who is much selective in telling their whereabouts. So as you can imagine, these two protocols have different scalability properties, where the directory-based is a more scalable protocol, but also different latency properties. So the Snoopy-based, the broadcast way of dealing with coherence, often can result in shorter delays in communication. So before I tell you how an upgrade is done in the Snoop-based protocol, so an upgrade we refer to as a point in time where a cache has a readable copy. This is readable but it's not writable because there are many shared copies. So an upgrade means you upgrade your permissions from a read-only to a read-write permission for this specific cache line. Before we talk about snooping, I want you just to try to recap what we did in the previous lecture and tell me what we need to do here to implement coherence on this write. So as you will see in this picture, what we need to do is to invalidate the cache to the left and the cache to the right. And we do this in this broadcast way by broadcasting to everybody in the world, everybody on this bus that happens to have a cache copy of A, please remove it from your cache immediately. The other way to implement coherence, the directory-based coherence, as I said, was a point-to-point protocol. You don't rely on the broadcast mechanism. Instead, the cache in the middle still needs to invalidate all the cache copies. So it will send a point-to-point message up to memory, and memory will figure out who may have a cached copy and send out invalidation messages to them, and eventually those copies will be destroyed. That we're going to talk about in the scalable implementations of cache coherence. So going back now to the Snoopy-based cache coherence, often Snoopy-based cache coherence relies on the fact that we have some kind of bus. So this is a media that can carry requests and data somehow, and it's a media where we have many caches hanging off it, even though on this picture I only show one cache hanging off this media. It also relies on the fact that we have some kind of per cache line state information. So inside the cache, so we instead, when we implement the caches, we sort of replace the valid bit that we've seen before with another couple of extra bits, so we can encode more state than just invalid and valid in the cache. So maybe 2 bits or 3 bits, so we can encode maybe 4 or more states in the cache. And this state is associated with each cache line in this design. We also have some state machines that defines what would happen if you see a invalidation request for a specific cache line. The state machine will do a lookup in the cache to see if the cache contains A, and it will do so by comparing the address tag and so on. And then it will look at the state, and the state machine will define what the new state should be for that specific cache line that corresponds to A. So we have a state machine for all the transactions we snoop on the bus from above. And also we have another state machine defining that will also do a lookup. When we do ordinary accesses from the core or from the CPU, those accesses will also, of course, do a lookup in the cache. And that state machine will tell how we should make transitions between different states for a specific cache line depending on what kind of accesses you do. And also that state machine defines what bus transactions you will need to send out for everybody else to snoop on. So here's a picture you actually have seen before when we talked about how caches are implemented. So we said that this is an 8-way set associative cache, as you may recall. There are 8 possible places where a piece of data can be stored, and in each of those places we have a cache line with some quite a large number of bytes, 64 in this example. We have some state associated with the cache line, and we have an address tag that we need to compare. We all remember this. So that comes to the next question. So please tell me which of these statements are true about the cache that's cache coherence implemented for a cache like the one we have here. So the cache line this coherence has to be kept at the cache line granularity because we only have one state associated with the entire cache line. So that's all we can deal with. Either the cache line is valid or invalid, or is writable and is readable, but the state gives the property of the entire cache line. So now we're going to look in a little more detail what those state machines are, what they may look like. So first of all, we're going to look at the state machines that snoops on the bus. So those 2 state machines here, they all sit on that bus, and for every transaction you send there, they will need to do a lookup in the cache to figure out if they have that cache line that is associated with whatever transaction sent on the bus, and also they need to figure out if there is some state change they need to do, and also if they need to reply to this request that they've seen on the bus somehow. So here we have a definition of such a Snoop state machine. So this Snoop state machine is called the MOSI state machine. And it's called MOSI because it has exactly 4 different states, M, O, S, and I. So the M state is a state that for a cache line in the M state, the following holds: that this cache has a dirty copy of this specific cache line, and it's the only cached copy in the system. So with dirty, we mean that the value stored in this cache is different from the value stored in memory because it's been updated or modified in this cache. State shared says that I have a clean copy of this cache line. So this means that, clean means that you don't have the obligation to write back this cache line to the cache, and it also implies that other caches may also have a cache copy of this cache line. Owner is sort of a mixture of both. It says that this cache line resides in the cache, but it is dirty. It's a dirty cache line. But at the same time, there may be other cache lines as well. So this may, for example, apply to the cache in the middle. The cache in the middle that first performed the write, and then the cache to the left requested a readable copy. So the cache in the middle did a cache-to-cache transfer. After that cache-to-cache transfer, the cache in the middle will be in this O state. And then, of course, it's the 4th state, which is invalid, which implies if you have the cache line in your cache, but the state bit says invalid, that means that it's not a valid copy. Also, if it's a cache miss, so you don't even have the cache line, that also implies that you have the cache line in state invalid. Those 2 things are equivalent when we talk about cache coherence protocols. So now we're going to look at the different bus transactions, the transactions you may have on the bus and that you may snoop. So these are transactions sent from other caches. So first we have a bus RTS. So this is a transaction called the read to share RTS, and it simply says that some other core or CPU in the system is reading the data and they got a cache miss. So now they broadcast to the whole world, I missed my cache, please give me a readable copy. Here we have one definition that says what we have to do if we are in state modified, state M, and we see such a bus transaction, bus RTS. So the way you define these transitions in state machine is you put the input signal, that's a signal that you've seen on the bus, we've seen on bus RTS, then you do it slash, and then you say what output signal you have to do. This defines that if you're in state M, you see bus RTS, you're going to go to state O, and you will have to provide the data to whoever asked. So this is what the middle cache will do. The middle cache that first modified its cache line, so that means it modified the cache line, so it's going to end up in state M, because it's a dirty copy of the cache line, and it's the only copy in the system. So after the middle, right, here we are. Now the middle sees the read request from the left cache line, so it will see bus read to share request. It will have to provide the data, the cache to cache transfer, and it will need to go to the O state, saying, I still have a dirty copy of my cache line, which means I still have to perform the write back, but I also reckon the fact that others may have cached copies as well, so you no longer have write permission. If you're in state O and you see more read to share requests, that means that you will have to reply to them as well, because you still are the one with the dirty data in your cache, which is different from the one in memory. So you will have to provide the cache to cache transfer, but you don't need to change the state. So you just sort of loop around here. That's what this circle symbolizes. Stay in the same state, but still provide the data. If you're in state shared and you see an RTS, bus RTS, that means you don't do nothing. You just stay in state shared and you don't have to provide any output signals. And of course, if you're a state invalid and you see a read request from somebody else, that's none of your business. So you're going to stay in state invalid. Bus read to write, that means that somebody who didn't have this piece of data before, but some other core that didn't have this piece of data before, but wants to make modifications to this cache line, they would like to read the data, but their intention is to modify it right away. They need their entire cache line, but they may only want to change one word of it, but still they need to read the entire cache line, because after they've written the cache line, all the other words of the cache line must be valid. So read to write. So if you are in state, let's say, modified, and you get a request read to write, somebody else wants your data, but then they're going to modify it right away. So that means you're going to provide a state transition to state invalid, and you will provide the data when you make the transition. And the same thing will happen if you are in state O. You're still the owner. You will provide the data if you see read to write request, and you will have to end up in state invalid. If you're in state shared, you don't have to provide the data, but this state machine still defines that you will have to make the transition from shared to invalid. So everybody goes to invalid whenever they see a read to write request. Bus invalidate is sort of like read to write request, but this is from a core that already has a cached copy in its cache, but that cached copy is not a writable copy. So it needs to get a write permission to a cache line it already has in its cache. So all it needs to do now is to nuke all those other copies in the world. So it sends out bus invalidation request. So what happened to us if we see in bus invalidation request? So if I'm in state shared and I see bus invalidation request from somebody else, that's a no-brainer. I will have to go to state invalid. If I stay in state owned and see bus invalidation request, the same thing. I have to go to state invalid. I don't have to provide the data because that the requester already has a copy of the data. That's why it's sent a bus invalidation request. If I'm in state invalid, I could care less. Just go on or fight about this cache line. I don't have it, so I don't care. So we just stay in that state. However, if you look at this picture here, there is no definition of what happens if you're in state modified and you see a bus invalidation request. So the question to you is, why is there no bus invalidation arrow going away from state M? And that's, of course, because it's impossible that there would be any other system, any other cache that has a readable copy. Since we are in state M, definition of M says this is the only cached copy. So if we have the only cached copy, no one else can have a cached copy, which means nobody else would, it wouldn't be possible for anybody else to send out a read invalidation, a bus invalidation request, because that required you to first have a copy of the cache line. Finally, we have the bus write-back. So bus write-back, that's when you write back dirty data to memory. And that, of course, you have to do if you have a modified piece of data in your cache. You will have no, wrong line of thought. Back up. So if you see a bus write back from somebody else, what are you supposed to do? Well, if somebody else does a write back and you have the cache line in state shared, you don't care less. He took care of his business. So this would be, for example, the cache line, the cache to the left that will see the write back from the cache in the middle. Will do nothing. And if you are in state modified, it's impossible for you to see a write back, because if you're in modify, you have the dirty data, it's your responsible to do write back, so you will not see anybody else do write back. So that once more is why you don't have an arrow going away from state modified, and also why there's no arrow going away from state owned defining what to do for a write back, because once more those are impossible things to happen in the Snoop state machine. So that was the Snoop state machine. And now we're going to look at what we call the CPU access state machine, what that defines the actions, the state transaction actions you will have on the cache in response to some action that your CPU will generate. So if your CPU will do read or write, what kind of bus transaction will you generate depending on the state, and what state changes will you do to the cache line. Once more, it's a MOSI protocol. It's, of course, we have the same states as before, but the state transitions now look very different. But it's, of course, exactly the same states. There are three kind of actions that we'll talk about right now that the CPU may generate. One is a CPU read transaction. So that's caused by the fact that the CPU performs a load instruction to variable A, or to a variable that resides in the cache line A, and now this state transaction defines how you should change the state for the cache line A, because you got that request from your own CPU. So here, once more, we have the in signal / out signal defining the state transition. So if you're in state invalid, cache line that it's a cache miss, or the cache line actually exists in your cache, but the state bits encode that you're in state invalid, then this says CPU wants to perform a load. That means you are going to make state transition to state shared, and you're going to send out a bus read to share request. Okay, and we recognize this from the previous state machine. So these are the transactions that could be snooped by everybody else. If you're in state shared, and the CPU wants to read, well, there is no specific transition here for the cache, because you're going to stay in shared. You're also going to give the data to the requesting CPU, but that's not sort of part of the cache coherence protocol. The out signals here defines how you interact with other caches and not how you interact with your CPU yourself. In your in state owned, the same holds there. State owned implies that it's a readable transaction and you don't have to make any changes at all. And if you are in state invalid, and if you're in state modified, and you see a CPU read transaction, that means that you're going to take this little loop here, and so you stay in state modified, and things are cool. CPU write, so this is a store, or could also actually be caused by an atomic transaction. We talk about synchronizations. store transaction from the CPU, what will that do to my cache coherence protocol? Well, if you are in state shared, like for example, the cache in the middle in that simple example was in state shared and its CPU wanted to do write transaction. So this defines, the protocol here defines that you should make a transition from state shared to state modified, and you need to send out the bus invalidation signal because you need to invalidate all your other cache buddies out there. If you're in state owned, so state owned is still not a writable copy, it's just a readable copy because there may be other cached copies out there. So there also you have to make a state transition to modified and send out the bus invalidation signal. And if you're in state invalid and you want to perform a write, that's when you have to send this read to write transaction saying I want a copy of that cache line and my intention is to modify that cache line as soon as I get it. So it's sort of combination of a read to share and an invalidate in the same transaction. And finally, if you are already in state modified and you want to perform a CPU write, you're cool. You can let that store happen without telling the rest of the world about it. Finally, the last transaction that may be caused by your CPU is that there is a replacement of a cache line. So this is, not this cache line is not accessed directly by your CPU, but some other access that the CPU performs forces this cache line to be replaced. So what you will have to do then, if you're in state modified, is that when you have to perform the bus write back to update the memory. Likewise, if you're in state owned, that also have a dirty cache line, so you have to update memory and go to invalid. If you're in state shared, you get a replacement, you simply go to state invalid because it's going to be removed from the cache. So next time you try to access it, it will be cache miss, which corresponds to state invalid. So there you have it, the implementation of the write back as well. So what we defined so far is actually the entire cache coherence protocol. It's a MOSI protocol. There are other protocols we will discuss as well, but this is good enough implementation. It's actually a very efficient way of implementing cache coherence we have defined now. So now you understand how the cache coherence protocol is implemented will understand what actions to take when the write is performed. When you perform this write operation, the state up here will be in state of this cache line will be in state shared, and that cache coherence protocol sitting between the CPU and the cache will say, whoops, I cannot write to a shared cache line, and that coherence protocol says I better send out an invalidation signal. And the other caches will have some kind of Snoop state transition, snooping, or that bus invalidate, and that state transition diagram will tell us that we need to go from state shared to state invalid, which in essence will destroy those copies. After that has happened, we can modify the cache line in the middle, and now that cache line will be in state modified. So in summary, it could be actually interesting for you to know that the concept of snooping cache coherence was first suggested here in Sweden. It was the ISCA conference, which is one of the absolutely most prestigious conferences in computer architecture. And that was held in Stockholm in 1984. And it was suggested by a professor from Wisconsin called Jim Goodman, which it happened to be the opponent when I got my PhD myself. Jim Goodman was also the advisor of one of the other professors in the architecture group, Stefanos Kaxiras. So this is a person we know quite well, and he's alive and thriving, and he got one of the most prestigious, I would say he got the Nobel Prize for computer architects last year for his discovery. Snoopy can be used to very effectively implement cache coherence, and it's done by broadcasting information on every read and write miss in your cache. And here a read miss and the write miss it has slightly different definitions. The write miss is a write attempt to cache that could not be completed. So, write attempt to cache line in state shared. Snoopy coherence is best suited for on-chip coherence between a small number of caches. It's not that suitable if you implement coherence between chips, and it's not that suitable if you have a large number of caches because of the Facebook effect here. You just have too many friends telling you too many irrelevant things going on, and you just don't have enough bandwidth to do all the necessary Snoop lookups in your cache by yourself.